This video acts as an introduction into polar form for complex numbers. And in this scenario, we're dealing with the first quadrant. It gets a little bit more complicated later on when we have points in other quadrants. But if we take a look at what we're given here, we're given the point 1 plus root 3i. That is written in what we call rectangular form. And why is it called rectangular form? Well, if I was to follow the instructions to plot that point, I would be going out a distance of 1 according to the rectangular form, so go out 1, and then root 3i means go up root 3 in the I direction. So I'm going to get us up to root 3 in the I direction. Now root 3 is approximately 1.72, so I've just plotted above 1.5 and just below 2. So that's rectangular form. It described it using two pieces of information because it's in 2 dimensions. If I'm going to describe it in any other way, I still need 2 pieces of information. And we can do it using, I like to think of it as a string and an angle of rotation. So what I'm now going to say, instead of talking about the go out this many, go up this many in rectangular form, I'm going to say attach your point to the end of a string. And you can find out how long that string is. That would be r. It's called the modulus. So you would have come across it before in a few other areas of the course. In polar form, it's going to be represented by the letter r, which can also stand for the radius. And you'll see why in a second we refer to it as that at times. So r is our piece of string. And what I'm saying is you're going to take that piece of string, that's a length r, and you're going to rotate it around until you hit that point. So I needed to talk about 2 things there. I needed the length of the piece of string, and I also needed the rotation. So I need to know how many degrees or how many radians do I need to turn that string anti-clockwise. If you noticed, I'm working anti-clockwise here. How many degrees is it? So I'm going to call that theta. And that rotation is sometimes called the argument. And it's why over here I've written it as a little checklist. Every time that I want to go from this over here, which is our rectangular form, into this over here, which is our polar form, I need to find the modulus, the length of the piece of string, and I need to find the argument, the rotation around. How am I going to find that information out then? Well, if you take a look at the diagram that we have, we are really looking at a right angle triangle. That's all that it boils down to. It's become a triangle who's got a base length of 1. So let me go down here and sketch it out. So we've got a base length of 1 and we've got a height of root 3. So I'm going to draw that in. So that's root 3, the base length was 1, and I also have a radius to find, that r, also known as the modulus. So the modulus, which is this length of our string here, I'm going to give that the letter r, and I also had to find our rotation, which was the angle in here. Now if I gave that to you when you were in 2nd year or 3rd year, whenever you did trigonometry, and I asked you, find the length of the side labelled r, I'm fairly confident you would have been able to do it. So if you take a look at what's going on here, that's a triangle. What type of triangle is it? Well, to ensure that that was root 3, the same distance that I'd gone up, I would have had to have drawn that at a 90-degree angle because it had to be parallel to the imaginary axis. So that's 90 degrees inside here. Those 2 lines, the pink and the blue, those are perpendicular to each other. So it's a right angle triangle. Then you go through your formula in your head. What have I got to deal with right angle triangles and missing sides? Well, that comes back to Pythagoras' theorem, doesn't it? So Pythagoras' theorem, what is it? How do I use it? So I'm going to write it down first. It's c squared is equal to a squared plus b squared. C is always the side that is opposite to the right angle. It's the longest side, yes, but how do you identify the longest side if you don't know all of the side lengths? How do you know? Well, it's the side opposite the biggest angle, and the one that is the biggest angle in a right angle triangle has to be the 90 degrees. So I'm going to have C, which is our R in this case. How did I know? Again, opposite the right angle, C is the hypotenuse, which is R in this case. So R squared is equal to A squared. Now, it does not matter what you call A and B. It really doesn't matter. The one that's really important that you do get right is that you get your C right. That's important. Now what's important is that you make sure that you use good notation, that you fill things in brackets. I usually like to do it for negative numbers and surds, but really if you were getting into good habits you would always put it in brackets and then you would never forget it and you wouldn't have to remember the special cases. So there, I've put it in brackets and I'm going to square it out. Now what I'm going to do is I'm going to work my way through it. It's now just an algebra question. So I've got R squared is equal to 1 squared, which is just 1. So let's write R1 down. Then it's going to be plus root 3 squared. So root 3 squared is going to be, well, that's actually doing and undoing, isn't it? Because it's square rooting and squaring. Those are the exact opposites of each other. They undo each other. Then what we have is 1 plus 3. Well, 1 plus 3 is just equal to 4. So I get R squared is equal to 4. And how do I undo squaring? So if I want to get rid of this square, I'm going to square root both sides. So I get the square root of 4. So I get R is equal to 2. So I've now actually figured out how long the piece of string has to be to write my answer in polar form. Okay? So our piece of string has to be a length 2. The other thing I need to find then is the argument, or the angle of rotation. So how am I going to find that? Well, I've again a right angle triangle and I want to find out the angle. So you go through your formula in your head and you think, oh, it must be SOHCAHTOA, or sine, cos and tan ratios. But which one am I going to use? Technically, you have all of the information for all of the sides now that you found R. But what I would always recommend is, just in case you got R wrong, or you fumbled it at the end, or you put it into the calculator wrong, or you've a rounding error, I would usually recommend that you use the two sides that were originally given in the question. And those two sides happen to be this side, which is opposite to the right to the angle that we're going to use, and this one, which is going to be adjacent. It's next to the angle that we're going to use. So which trig ratio deals with opposite and adjacent? It's going to be tan. So I've got tan of the angle is equal to root 3 all over the adjacent, which is going to be 1. So I'm going to put that all over 1. Now, how do I undo the tan? How do I get rid of tan? Well, to get rid of the tan on this side, I do the opposite to undo it, which is tan inverse. And whatever I do to one side, I'm going to do to the other. So tan inverse of the other side, which is root 3 over 1. Root 3 over 1. Now you can put that into your calculators, or you might remember this is one of the special angles that we have, special ratios that we have in our log tables on page 13. And when I look up root 3 and I look it up in the tan row, I'm getting that the column that matches it is 60 degrees. So I now have the two pieces of information that I require to write anything in polar form. I do know the modulus and I do know the argument. And now I just piece it together using this formula. So it's going to go R by cos of theta plus I sine of theta. And be very careful, make sure you have your brackets, that's quite important. What we have now is we're describing that point in space in terms of it revolving around a pole, the pole being the origin. So you're connecting your string, which is a length of 2, to the pole, and you're rotating it anti-clockwise 60 degrees. And if you do that, you should hit the exact same point in space as 1 plus root 3i. So to finish off the question, just to write out what it looks like for us, I'm going to have r, which is actually going to be, we know, 2. So I'm just going to write out the formula so you can see what I'm doing. R is going to be 2, and then I've got cos of theta, which is going to be 60, so I can write 2 by cos of 60 plus I sine of 60. And that's it. That's now the equivalent of 1 plus root 3i in polar form. It describes the exact same point in space, but using two different pieces of information. And the nice thing about it is you can check that you've got it right. You can check if you put into your calculator 2 multiplied by cos of 60, so you do 2 by cos of 60, you should get out 1. And we do. If I do 2 multiplied by I multiplied by sine of 60, now you'll know you can't put I into your calculator, so I'm going to use the commutative property. I'm going to move it around. I'm going to say it's 2 by sine of 60 by I. And we can even use the associative property of multiplication and do this first and then multiply by I. And if you do 2 by sine of 60, you will get out root 3, and then you multiply that by I, root 3i. So that's a very kind of brief introduction to polar form. As I said, it gets a little bit more complicated as we move into different quadrants. So do take a look at that second video introducing polar form that I have on my channel.